So in sorry, keep the earphones.
Start channel. Start channel.
Start and
Slide it.
scroll.
Next slide it.
Scroll.
So today I'm going to speak about Java virtual machine. Okay, and we'll speak about Java programming language, Java virtual machine, and Java API, application programming interface. Okay. Next one is why Java is has gone very famous for internet. So this is the concept of bytecode. The bytecode generated by the Java front end is an intermediate form. One is compact, another is platform independent. For example, the Java program, if you compile, we will get dot class file. And then what is this dot class file? This dot class file contains bytecode. Okay, this bytecode is only understood by the JVM. Okay, and JVM will, depending upon your platform, that is your Linux or Windows or any other operating system, it will try to generate the instructions. Those instructions are, what do you say, understand by your uh, platform or operating system or your microprocessor. So whenever a Java program is generated, and when you compile you will get dot class file, and this dot class file contains a set of instructions that is in bytecode. Bytecode means 1 byte. So each instructions generated is 1 byte, that is nothing but 8 bits. So whenever it is generated, so what happened, so either we are going for Linux or Windows. So this JVM will try to convert this instructions, which is understandable by your or operating system or your processor. Okay, suppose if you take C, what happens when you compile C, it will be compiled to object file. You will get an object file. Okay, and after when you compile this when you execute this object file, we'll get executable file. And when execute is executable file, it is platform dependent. Okay, why? Because the same executable, what you have executed in C, the same file, if you take in the other system, which is having completely a different platform, that is Linux or Windows. So what will happen? That is dependent. It is platform dependent. It will not understand. Suppose you have executed in Linux platform and you are taking the .exe file of the same program and you are executing in your Windows operating system. But the instructions generated by that Linux operating system, it will not be understood by the Windows platform. So what will happen? So it is dependent. The instruction which is generated by Linux operating system, it will be understood by the operating system by the Linux. If you generate your code, if you execute those set of instructions in Windows platform, it will not try to understand. So because of this bytecode concept, Java is very much it has got it has been worldwide famous because of the bytecode concept. Okay, next one is next topic is, we'll see here phases of compilation. First we will give the character string scanner. Then what will happen? The scanner will convert to the token string. Again from the token string it will go to parser. From the parser to parser tree, then it will go to semantic analysis. From semantic analysis to abstract syntax tree with annotations. And this will be again input to intermediate code generation. From the intermediate code generation, again the graph flow with pseudocode instructions in the basics block, it will go to the machine independent code improvement. And then again we have this from again graph flow pseudocode instructions is basic block. Then we'll give this into machine independent code improvement. And this input, again what the output will get is modified flow chart, and from this modified flow chart again the input is target code generation. Again, the target code generation, the output will get as assembly language. And this assembly language, if we give the input, it will be machine specific code improvement. Again, the output will get real assembly language. Okay, these are the phases of compilation. Okay, then here already I explained. The first your what do you call the Java, you write the Java program with .java as an extension, and this when you try to compile it, you will get a class file. What is then class file? Before I told you that class file contains bytecode. Okay, so this bytecode, your local or remote will load this. Okay, using class loader. Class loader in Java virtual machine will load your class file. Okay, so all the class files will be loaded by class loader. Okay, and then this bytecode will give to the execution engine. Okay, and this execution engine will give to the host operating system. Okay, so suppose you have some native method invocation. Native method invocation means some of the code is in, so for example, C or C++ language. So those will be taken care by the host operating. Suppose you wrote a program Java and you have some of the code which is already written in C, C++. So that type of code you want to be executed in this Java environment. So all these things will be taken by the native method invocation. Fine. Okay. And this is all about then execution engine, the backend transformation and execution. Simple JVM bytecode interpretation just in compiler. We have here two things. One is interpreter, and then next line we have compiler. So we have two things: compiler and also just-in-time interpreter and just-in-time compiler. We called it JIT compiler. Okay. So what is the missing in any other you see in C++ or in other languages? We have only one thing. Either you have a compiler or you have a interpreter. Okay. So, but we have here both. Okay. For example, you take any looping concept. For example, if I say for I is equal to this I loop, we say I is equal to 0, I less than equal to 10, and I plus plus, and we write a print statement. So this print statement will be going for 10 loops, for example. So just in compiler, what it will do, it will copy the whole code. It will copy the whole code in the memory itself. First, it will compile the program and it will compile the statement, and that statement will be copied to the memory, the whole code, the bytecode will be copied, and each time interpreter job is each line it will try to convert into machine language. Instead of each line will be compiled into machine language, that the code itself, the looping code itself will be copied into the looping code, which will converted into class code, will be copied into the machine directly, and from there only 10 times the loop will be executed. And that is the beautiful concept of just-in-time compiler. Otherwise, what will happen? The 10 lines, the repeated 10 lines, print A for 10 times. So what will happen? This repeated code, each time it will be taking 10 from the memory, it will be fetching and it will try to execute. Again, like 10 times the fetching from the memory is required. So again, it will take the next line and it will try to print again next line. So each time fetching is there. So 10 times you need to fetch from the memory and execute. But just-in-time compiler, what it will do, just-in-time compiler directly will copy the code into the machine in the memory, and it will fetch it from the memory one time, and it will try to execute that printf statements for 10 times. Okay, so at a time it will try to see the for loop and spend. So these are the looping things where we'll give that kind of code to just-in-time compiler. And the machine code is cached for subsequent invocation, and it requires more memory, as I told you, because the whole code is copied once only, and it will fetch once, and that the same in the loop that printf will be printed for 10 times. Then adaptive optimization. The interpreter monitors the activity of the program, compiling the heavy used part of the program into machine code. Okay, it is much faster than simple interpretation. The memory required is only slightly larger due to 20 to 80% rule of the program execution. In general, 20% of the code is responsible for the 80% of the execution. So here actually the whole scenario is that I told you earlier also, these class files, whenever you execute the Java file, it will try to convert into dot class file. This dot class file who will load into the system is the class loader subsystem. After that, we have certain, in the memory, we have certain runtime data areas. Okay, method area, heap area, stack area, program counter registers, native method stacks. So in native method stacks, what will happen? I told you earlier, just now in C, C++, some native method language, the program is written. Those will be handled by native method stack. Those kind of programs, all the data will be put in the native method stacks, which are in C, C++. Okay, those are native methods. And we have program counter registers, Java stacks, heap area, the method area, where actually our program, all the variables are stored in method area. Okay, then you have the execution engine. So, and then we have native method interface, and then we have native method libraries. Fine. This is what. So you have shared areas. Okay, in method area, what all the things we can have? We have a class data. Okay, in the class, whatever we have, for example, your methods, and you have data members. Members is nothing but your variables, whatever you declare. For example, int I and the int j or character string, all these things which is there in the program, the member functions and the member variables will be stored in the method area. And heap, where the object is created. So all the objects will be, the data will be stored in the heap. Okay, now here we have thread data areas. So before going to the thread, let me explain. Thread is nothing but, so when a large quantity, when you have a huge program and you have different methods for executing different things, okay, and again you club the result. Also, what will happen? So what is thread is a very lightweight. It is a process. Okay, it is a program which will handle one process. Okay, suppose we have in a program 3 processes. So thread 1 will handle one process, thread 2 will handle one process, and thread 3 will be handled and the process. So like this, we'll divide, and threads will be handling those processes simultaneously. Okay, so we have for the thread 1, we have the 3 things: stack frame, stack frame, stack frame. All these things. Thread 2 also we have stack frame, and thread 3 also stack frame. So in threads will be kept in Java stacks. Okay. And after that, in thread 3, native method stacks. Whenever we talk about native method stack, it is nothing but the native methods will keep that. It is not in Java language. It's nothing but a method. For example, C, C++. Okay. And this stack frame has 3 parts. One is local variables, one is operand stack, and one is the frame data. Local variables, before that I told you that in the stack frames, we can store the local variables, whichever we declare. For example, int j, and all these things. And we have an operand stack. Okay, where we store the variables A, B, C, whatever, and we also have the frame data. So stack frame has 3 parts. One is local variables, operand stack, and the frame stack. Now you see, it's very clear in the local variables. For example, see in this, they have stored in run class method. Type is int, long, float, double. Okay, and all these things are being stored in the local variables are stored in the this kind of stacks. Okay, we can see here example 3a, public stack in run class method, int I, long, L, all these things, okay, will be stored in the stack. Okay, and then we have here operand stack. Okay, the operands which will try to load. For example, A is equal to 100 or B is equal to 10. The values will be loading in this operand stack. Okay, before starting, and you can see here when we are going to add 2 numbers here, I load 0, I load 1, then you add the 2 load registers, whatever you kept, and then you store in the I store 2. Okay, fine.